Okay, in our previous lecture, we talked about the principle of stationary total potential energy, and we illustrated that with a simple spring model. What I want to do in this lecture is basically extend that so that we can talk about the potential energy of an elastic body in 3D, and then we can apply that same principle here. So this is kind of completing that discussion. Okay, so we're going to, having introduced this idea of the potential energy of a system, we're now going to turn to the potential energy of an elastic body. Okay, so just like we had with the spring, the potential energy is going to consist of the strain energy plus the potential energy of the applied loads. Okay, so let's see if we can remember how we define the strain energy density of an elastic material. So let's say recall the strain energy density, and remember what strain energy density is. That's the strain energy per unit volume. Okay, so the strain energy density of an elastic material is given as follows. We define that strain energy density as U naught, and that's going to be equal to the integral of sigma ij d epsilon ij. Okay, let's call that equation 1. Okay, for a linear elastic material, we have the constitutive law given by, we would say sigma ij is equal to c I j k l epsilon kl. Right, let's call that equation 2. So substituting equation 2 into equation 1 and then integrating gives the following. We end up with U naught is going to be equal now to the integral of c I j k l epsilon kl d epsilon ij, which looks a lot like our 1D integral, and we can write this is 1/2 epsilon ij epsilon kl, which is effectively epsilon squared, c I j k l. Right? Call that equation 3. So that's the strain energy density. The total strain energy in the body is given by integrating that quantity, U naught, over the volume. Okay, and when we do that, we end up with that U is equal to the integral of U naught dV, which is going to be equal to 1/2 times the integral of epsilon ij epsilon kl c I j k l dV. Call that equation 4. Now we want to consider the potential energy of the applied loads. Okay, so the first applied load we'll think about is the body force. So for body force, we'll call it B sub I. Right, so there's the vector quantity. The potential energy is given by negative integral ui bi dv. Right, and that negative is because it's an applied load, and as we move through the distance ui, we reduce the potential energy of the system. Okay, so let's call that equation 5. Okay, and now let's think about the potential energy of the surface tractions. Okay, and we'll say those surface tractions, we'll call them T sub I. The potential energy in this case is given as follows. Same thing here, we have a negative integral of Ti ui ds now, right, because it's a traction on a surface. So maybe I should put that this is over the portion of the surface that has a traction boundary, right? So that would be the potential energy contribution from the tractions. Let's call that equation 6. So adding equations 4, 5, and 6 gives us the total potential energy of an elastic body. So we define that, remember, as capital pi. So pi, total potential energy of the elastic body, is going to be equal to the integral over the volume of, let's see, this is 1/2 epsilon ij epsilon kl c I j k l dv minus integral of ui bi dv minus the integral over the of the surface where the tractions are prescribed of Ti ui ds. Let's call that equation 7. Okay, so now we've defined the total potential energy of an elastic body. I want to remind you of the principle of stationary total potential energy. Okay, so what did that say? Okay, it states the following. It says that the function that extremizes the functional given by equation 7 is going to be the one that satisfies equilibrium. Okay, so let me just describe the strategy that we want to use here. We can define equilibrium in its strong form, right? Which you can get just by doing a force balance, let's say on a volume element. But we could also, we showed this many lectures ago, we can also take that strong form and we can convert it into a weak form. The weak form of equilibrium is often defined as the principle of virtual work. So what we're going to show is that when we extremize this functional, we recover the principle of virtual work in this case. So let's go ahead and extremize equation 7 by taking the first variation and setting it equal to 0. So here we go, delta pi equals 0. And what is delta pi? Well, we have a 1/2 integral over the volume. And then in this case, obviously CIJKL is a constant, so we end up being able to use a product type. Remember, we're not taking a derivative, but we can use some of those same rules. So this becomes delta epsilon ij times epsilon KL CIJKL plus epsilon ij times delta epsilon KL CIJKL. Okay, that quantity integrated over the volume, dV, minus integral of BI delta UI, dV, minus integral over the traction boundary surface of TI delta UI, ds. And we're going to call that equation 8. Okay, so this obviously doesn't yet look like the principle of virtual work like we've talked about before. So let's consider the term epsilon ij delta epsilon KL CIJKL. Okay, and hopefully by this time in the course you're able to manage this, but sometimes it's easy to forget if we haven't done it in a while. So we can first, let me write that down here. So let's say that this is equal to something, right? So epsilon ij delta epsilon KL CIJKL is equal to what? Well, we can say that CIJKL is symmetric in both ij and KL. We can swap those, right? So I'll just say is equal to, and this is by symmetry of ij and KL. So this then can be written as epsilon ij delta epsilon KL. Nothing changes there, but this is the same statement as saying C KLij, right? That's just part of the symmetry that emerges from this fourth order tensor. Okay, so let's call that equation 8. Sorry, equation 9 rather. Okay, but now I also realize that all of my 4 indices are dummy indices, right? So I'm free to swap those as I feel like I need to, right? So here's my next statement. Since all indices are dummy indices, we can relabel. Okay, and so now we can write epsilon ij delta epsilon KL CIJKL, right, is equal to, I'm just going to write this out again before I relabel, epsilon ij delta epsilon KL, now CKLij. Okay, now I'm going to relabel. So this equal sign was due to the symmetry of that stiffness tensor. This is simple because they're all dummy indices, right? So I'm free to call, I can call Ki now, and I can call Ik, I can call Lj, and I can call Jl, right? I'm free to do that. And I'm left now with epsilon KL delta epsilon Ij times CIJKL. Call that equation 10. Okay? So now I want to substitute equation 10 into equation 8. And when we do that, we end up with the integral over the volume of, now what's going to happen is that this second term now is the same as this term, so that gives me a factor of 2, cancels the 1/2, and I'm just left with the quantity Cij KL epsilon KL delta epsilon ij dv, right, minus the integral over the volume of b delta ui, sorry, there's a bi delta ui, dv, minus the integral over the portion of the surface with the traction boundary of ti delta ui ds. That quantity equals 0. Let's call that equation 11. Okay, we're almost there. Now I'm going to just substitute equation 2 into equation 11. If you remember what equation 2 was, it said that quantity must be sigma ij, right? So let's substitute equation 2 into equation 11. And we now end up with the integral over the volume of sigma ij d epsilon I, or delta epsilon ij dv, minus integral over the volume of bi delta ui dv, minus the integral over the portion of the surface with the traction boundary of ti delta ui ds is equal to 0. Call that equation 12. And this is the culmination. This, if you remember, observe, this is the principle of virtual work. Okay? Which is the weak form of the equations of equilibrium. Okay, so we just demonstrated that the principle of stationary total potential energy holds for an elastic body, in that if we can write the potential energy down and extremize that, it does give us back the equations of equilibrium. So that's going to be important as we talk about some of the methods that we're going to use for solving our elastic body problem. In particular, we're going to focus next on the Rayleigh-Ritz solution, and then move to extend that to a finite element approximation. So that's why we wanted to show this here, and hopefully you're now convinced that this idea of minimizing the functional, that is the potential energy, that minimizing that quantity is what gives us the solution to an elastic problem.